Let's begin by having our practice buffer problems in front of us. We'll need a calculator and our Appendix D as the tools that we'll use to calculate buffered systems. Appendix D will help us find the Ka values to use in the Henderson-Hasselbalch equation. The buffered solutions find a pH by knowing the pKa of our system plus the log of the ratio of the base over acid. Henderson-Hasselbalch is the equation of use to find pH of buffered solutions. And in our video notes, we went through the development of Henderson-Hasselbalch. Really is just a manipulation of a Ka expression of products over reactants. The conjugate base over its acid from the buffered solutions goes in the parenthesis. Let's model with practice 1. To calculate the pH of a buffer solution that's 0.12 molar in lactic acid, and 0.11 molar in sodium lactate. The acid value, 0.12 molar, would be placed on the bottom, and the conjugate base, the lactate ion, gets placed on the top. So, we need to calculate pH. Using the Appendix D, I start by finding lactic acid Ka value, 1.4 times 10 to the negative fourth. We need to take the negative log of the pKa, negative log of Ka to turn it into pKa, and we'll add that to the log of the ratio of the base, 0.11 molar lactate, over its conjugate acid, 0.12 molar lactic acid. So, on our calculator, we will need to hit out negative log of the Ka value we found, 1.4 e negative 4, plus the log of the ratio of 0.11 divided by 0.12 gives us a pH reading of 3.82 pH units. This number makes sense that lactic acid has a range in pH of about 3.82, the acid range on our scale. So a straightforward calculation, given the concentration of an acid and its conjugate base coming from the salt sodium lactate, we just plug it into the Henderson-Hasselbalch and pull out pH. Number 2, let's calculate the pH of a buffer formed by mixing 85 ml of a 0.13 molar lactic acid with 95 ml of 0.15 molar sodium lactate. This problem involves a little bit more work in the sense that we're adding volumes. The concentration of 0.13 molar lactic acid and 95 ml of the 0.15 molar sodium lactate create a new total volume. So, let's take a look at lactic acid, and using our dilution problem, N1V1 equal M2V2, we need to solve for the new molarity once we have diluted those two solutions. So if we started with 0.13 molar and 85 ml of the acid, what would the new concentration be once we've added the volumes together? So 85 plus the 95 give us a new total volume of 180 ml. Hitting for the concentration of the lactic acid after it's been diluted. 0.13 times 85 divided by 180 gives us a concentration of 0.0614. We'll need to do the same strategy for the conjugate base coming from sodium lactate. And again, sodium lactate giving us the source of the conjugate base, the lactate ion. Its original volume of 95 ml times the original molarity of 0.15 set equal to M2V2, where the new volume now is the added value of 180 ml. So, let's hit for the new molarity, 95 times 0.15 divided by 180 gives us a value of 0.079 molar of the conjugate base. So we're ready to plug into Henderson-Hasselbalch. We just had to do some dilution formulas first. We are looking for pH, and we need the pKa, which we looked up for problem 1, 1.4 times 10 to the negative 4th units, plus the log of the ratio of base over acid. The sodium lactate is the source of our base, 0.079 molar. The source of the acid, 0.0614 molar. And now we'll hit and find pH using Henderson-Hasselbalch. So negative log of our Ka, 1.4 E negative 4, plus the log of the ratio, 0.079, divided by 0.064, and our pH for this solution is buffered to be 3.95 pH units. Our third question on our buffered worksheet reads, a buffer is prepared by adding 5 grams of ammonia and 20 grams of ammonium chloride to produce enough water to form 2.5 liters. We'd like to know the pH of our solution. So, knowing that, we'll need the Henderson-Hasselbalch, that pH is equal to pKa plus the log of the ratio of base over acid. We have some molarity work to do. We begin with 20 grams of ammonium chloride, NH4Cl, and we also have 5 grams of ammonia. Ammonia, of course, would be working for molarity of base, and ammonium chloride is going to give us its conjugate acid, the ammonium ion. So the conjugate pair in this buffered system is ammonia and its conjugate acid, ammonium. We'll do some molarity calculation by taking grams over molar mass over liters to find big M molar solution. So I'll hit for the molar mass first of ammonium chloride. 14 for the nitrogen, 4 more on the hydrogen, and 35.5 for the nitrogen, or the chlorine, and I get 53.5 grams as its molar mass. Let's also just place that over the volume of solution, 2.5. So hitting for the molarity of ammonium chloride, I hit my 20 grams, divided by my molar mass of 53.5, divided by 2.5 liter units, and my screen reads 0.1495. Let's make that 0.15 molar solution. On to the work for the base. 5 grams over the molar mass of 17 for ammonia per 2.5 litered solution. And calculating its molarity, 5 divided by 17 divided by 2.5 liters, and I have 0.1176. Let's make that 0.118 molar for the base. pH can be found by taking the pKa plus the log of the ratio of base over acid. However, this conjugate system using ammonia has a Kb value. Using the Appendix D for ammonia, it actually is listed in the small table for the Kb values, first in the list, as 1.8 times 10 to the negative 5th. But when I use Henderson-Hasselbalch, I must have a pKa value, so I'll let the calculator convert for me. Using the ion product constant for water, 1 times 10 to the negative 14th, dividing out the Kb value of 1.8 times 10 to the negative 5th, changes the Kb into the Ka. So pKa of the system is negative log Kw over Kb, plus the log of the ratio of base over acid. The base here is ammonia. Its concentration was determined to be 0.118 molar. Set over its conjugate acid that came from the ammonium chloride solution, 0.15 molar. So here we go, clear screen. We'll hit negative log of the ratio of Kw divided by Kb. Negative log of 1e negative 14 divided by 1.8 e negative 5, plus the log of the ratio of 0.118 divided by 0.15, base over acid, and we get a pH reading of 9.15 pH units. That number makes sense. This is a base, ammonia, so therefore it should end up with a pH greater than 7, and this does, so the number makes sense. It is a buffered solution, so in letter B, it's asking us to consider a net ionic equation, or a complete ionic equation, for the reaction that occurs when a few drops of strong acid, such as nitric acid, are added to the buffer. Remember the conjugate pair of ammonia and the ammonium ion. This is our buffered pair of conjugates. If I add a strong acid to a buffered solution, an acid will react with the base. Considering what we're showing, nitric acid is HNO3. It must react with the base from the conjugate pair, ammonia. Alrighty. Now, eliminate the nitrate ion and simply show the acid as the proton H+. Nitrate is a spectator and is just simply thinking about the net ionic equation. When hydrogen ion, the source coming from the strong acid, reacts with a base from our buffered system, we transfer the proton and simply produce NH4+, the ammonium ion. So in this particular equation, H+ added onto the base, NH3, we know that addition of strong acid produces more of the conjugate acid and consumes the base from the buffered system. And in the letter C, what happens to the buffered system when we add a strong base, such as potassium hydroxide, to the buffer? And again, if the buffered partnership is ammonia and its conjugate acid ammonium, potassium hydroxide is a strong base. A base reacts with the acid in the conjugate buffered system. So let's consume hydroxide with the ammonium polyatomic ion. The base reacts with the acid from our buffered pair. Again, think proton transfer. We will produce ammonia and a water molecule. The proton transfers from the acid to the base. Acids are proton donors, bases are proton acceptors. So we form more base when we add a strong base. Our next example, number 4. How many grams of sodium lactate should be added to 1 liter of a 0.15 molar lactic acid to form a buffer solution with a pH of 4.00? We'll assume that no volume changes occur during the process of adding the conjugate base of the lactate ion. So we have a buffered system containing an acid with its conjugate base lactate. The Henderson-Hasselbalch will show pH is equal to pKa plus the log of the ratio of base over acid. The sodium lactate is the base, the conjugate base of our lactic acid. The base becomes the variable we'll pull out using the Henderson-Hasselbalch, and from there we can use molarity problems to find grams. So we'll begin. The pH given to us, 4.00. pKa, remember P is just for saying negative log. The negative log of the Ka of lactic acid. We've looked that up before, and I'm just pulling that from problem 1 above. 1.4 times 10 to the negative 4th pH units, plus the log of the ratio of base, which we don't know, but we do know the acid to be 0.15 molar units. Let's simplify so far. We have negative log of 1.4 E negative 4. That's getting a pKa value, and that to me is 3.85. So what we'll need to do now is just 4 minus that answer to bring it to the left-hand side. So we have 0.146 is equal to the log of the ratio of base over acid, 0.15 molar solution. Remember to get rid of log, it sits on top. The opposite of log is a base of 10. So 10 raised to the power of 0.146 is equal to the concentration of our base over 0.15. The opposite of log is 10 raised to that power. So I'll hit 10 raised to the power of our answer, and that gives us 1.4 is equal to the base over the acid. We'll cross multiply for the concentration of our base. 1.4 times 0.15, and I get an answer of 0.21. What that's showing us is the concentration of the sodium lactate to be 0.21 molar solution. We need to do some molarity work to actually pull out grams. 0.21 molar is equal to X moles per liter of solution. So knowing that we have a 1 liter solution, cross multiplying, we also have 0.12 moles of sodium lactate, whose formula is provided as NaC3H5O3. We'll need a molar mass. Let me add that for us. Sodium is 23, plus 5 more on the hydrogen, 12 times 3 on the carbon, plus 16 times 3 on the oxygen. I found 112 as the molar mass. Mole times molar mass will solve for our grams of sodium lactate. Let me add the molar mass just to check my calculator. 23 plus 12 times 3 plus 5 plus 16 times 3. Yep, I got it twice. So I'm going to say it's 112 times the 0.21 molar solution, and that gives us a value of 23.52 grams of sodium lactate, NaC3H5O3. Our next problem, number 5. A buffer solution contains 0.12 moles of propionic acid and 0.1 mole of sodium propionate, which is its conjugate base, and that's been dissolved into 1.5 liters of solution. We're being asked to calculate the pH of our solution. Again, a Henderson-Hasselbalch, pH is equal to pKa plus the log of the ratio of the base over acid. We have to do a little molarity work. Moles per liter will contain our molarity. So let's just solve for moles of acid first. And if we look at the acid containing 0.12 moles over the 1.5 liters, I'll hit that 0.12 divided by 1.5, and I'm finding 0.08 molar for the acid, HA for acid. And its conjugate base is the propionate anion, C3H5O2 negative. Its number of moles, 0.10 mole over the 1.5 liter, pulls out molarity. 0.1 divided by 1.5, and this has a value of 0.067 molar units for the conjugate base. To calculate pH, we need pKa. Let me use my Appendix D to find propionic acid, listed in the P's. 1.3 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base is coming from the conjugate base here, sodium propionate, 0.067 molar units, divided by the concentration of our acid, 0.08 molar units, base over acid. Hitting for pH, we come up with negative log of 1.3 E negative 5 plus the log of the ratio of 0.067 divided by 0.08. This pH of this buffered solution is 4.81 pH units. Letter B. What is the pH of the buffer after adding 0.01 moles of NaOH? So, if we're adding a strong base, a base reacts with the acid. Let's consider the chemistry first. If OH negative reacts with lactic acid, I'll just simply write as HA, it is going to neutralize the acid to form water, giving me more of the conjugate base A negative. Remember, HA is standing for the lactic acid, and A negative is standing for the conjugate, the lactate ion, or propionic acid and propionate ion. Okay, so here's what we know. Before the reaction occurs, we know we have 0.01 moles of base, and we know that we have 0.12 moles of acid. Notice I'm using moles. Coefficients stand for moles, not molarity. And on the opposite side, the conjugate base coming from sodium propionate gave us 0.1 moles before the reaction occurred. The limiting reagent is hydroxide. So during the course of the reaction, it gets used to have no value left. It will also use 0.01 moles of the acid along the way. 0.12 minus 0.01 leaves me 0.11 moles of solution. And products get made to the same amount. 0.01 moles would be added, giving us 0.11 moles of the conjugate. So after the strong base has been added, we now see the number of moles of acid to be 0.11, and the moles of its conjugate base also to be 0.11. When we place this into the Henderson-Hasselbalch, we need the molarity units. So we'll need to remember to divide out the 1.5, although we're seeing that this will cancel out, but we'll show the work. 0.11 divided by 1.5 gives us a molarity of 0.073 for both the acid and the base. So pH is found using Henderson-Hasselbalch as negative log of the concentration of Ka. 1.3 times 10 to the negative fifth is the propionic Ka, plus the log of the ratio of base over acid, which we said both came out to be the same number, so we can see this portion just dropping out. So when they are indeed the same, pH does equal pKa. So we'll hit negative log of 1.3 E negative 5, and our solution now has a pH of 4.88, 4.89, rounding better. So here's what's happened. The buffered solution started at 4.81. We added a strong base, and it budged a little. It went from 4.81 up to 4.89 pH units. Letter C goes right with this same buffered system. Let's calculate the pH of the buffer after adding the strong acid, HI. So again, let's consider the chemistry. HI, again, let's just write that as hydrogen ion. The strong acid reacts with the base, A negative, and I'm using that to just represent propionate, the negative ion. And when it does so, we form more acid, HA. Adding a strong acid decreases the base and makes more of the acid in our buffered system. So here's what we know. Before the reaction, we had 0.01 moles of the acid, and the conjugate base was 0.1 mole. See how I'm pulling that from way up here? 0.1 mole of sodium propionate. And before the reaction, we had 0.12 moles of the acid, HA. Reactants get used and products get made. The hydrogen ion definitely is the limiting reagent and will be left with zero value. It will also consume 0.01 moles of the initial 0.1 mole of the acid. 10 minus 1 is 9, so 0.09 moles of the conjugate base are left over. And products get made, so we're going to be adding 0.01 moles to give us a new value of 0.13 moles in our new solution. Remember that when we use Henderson-Hasselbalch, it has to be molarity units, so remember to divide by that original volume of 1.5 liters. Let's calculate the pH after the addition of a strong acid. pH is found by taking the negative log of the Ka value, 1.3 times 10 to the negative fifth, plus the log of the ratio of base over acid. The base, 0.09 moles per 1.5 liter, is its molarity, and the acid has 0.13 moles over the 1.5 liters. Solving for pH. Negative log of 1.3 E negative 5 plus the log of the ratio, 0.09 over the 1.5 divided by 0.13 over its volume of 1.5. Now the pH is 4.73 pH units. Recall what's happened? We started with a buffered system that originally had the volume of 4.81. After the addition of a strong acid, it went down a little. Our number makes sense. Suppose we have to prepare a pH 4.8 buffered system, and we have the following choices. A 0.1 molar solution of the following. We have formic acid, which I see I forgot the D there, formic acid, and its conjugate sodium formate. So choice 1. Choice 2, I see we could use propionic acid and its conjugate coming from the salt of sodium propionate. Choice 3 is phosphoric acid and its conjugate coming from sodium dihydrogen phosphate. Which solution should we use, and how many mils of each solution would you use to make approximately a liter of the buffered solution? Well, let's start. Remember that the ideal situation is when the pH is equal to the pKa, and what that means is that the concentration of the conjugate base over acid is indeed the same. So the volume here really is irrelevant. It just means that we want the same concentration of each solution. So we want those to cancel out, so pH gives us pKa. And our target pH is 4.80. So let's begin by looking up some Ka values of each of these acids. In Appendix D, formic acid here it is, 1.8 times 10 to the negative fourth. So let's take the negative log of that and see what we find for pKa. Negative log, 1.8 E negative 4, and I get 3.74 pH units. I'll do the same for propionic acid. 1.3 times 10 to the negative fifth. Let's negative log for that and see what we get for pKa. Negative log of 1.3 E negative 5, 4.89. And one more to look up, phosphoric acid, and we'll use a Ka1 value since we have a conjugate there. 7.5 times 10 to the negative 3. So pKa is negative log of 7.5 E negative 3. and that gives us a value of 2.12. Knowing that the best match is when pH matches pKa within a plus or minus 1 pH unit, I can clearly see propionic acid being the best selection to make our buffered with a target pH of 4.80. How many milliliters of each solution would you use to make approximately a liter of the buffer? I think this is just asking us if we need a total of 1 liter, and the most important thing is to have this ratio the same. We better use the same volume to deliver the same number of moles of the acid and its conjugate base. 500 mils of the acid plus 500 mils of the conjugate base will deliver the same number of moles per liter of acid and base. It's important to make sure that pH and pKa are indeed the same, and they're just asking us to make sure that happens when the concentrations of base over acid cancel, and that happens if I'm delivering the same number of mole units. And it's clearly telling us the concentration of the acid and its conjugate is the same, so there's no trick here. If they were different, we would have to think about the number of liters per mole, but right here they're the same. So 500 of each gives us 1,000 mils total, and we have indeed delivered the same number of moles of the acid and its conjugate base.